Starting a jet engine is a far cry from simply turning a car key. It's not just about getting something running, it's about initiating a complex chain of events with incredible precision. It's a high-stakes, precisely choreographed process where every action has a consequence. The coordination and expertise required are immense. We're talking about igniting a controlled, continuous explosion, a miniature inferno contained within a sophisticated piece of machinery, inside a multi-million-dollar machine. The cost of failure is not just financial, it can be catastrophic. Every step, spin, fuel, spark, must be perfectly timed. A fraction of a second can be the difference between a successful start and a major incident. Get it wrong and you risk a dangerous, costly failure. The consequences can range from minor damage to complete engine destruction. The tolerances are razor thin, and the forces are immense. We're talking about pressures and temperatures that would instantly destroy most materials. Imagine building a house of cards in a wind tunnel. Every part must work in perfect harmony. It's a symphony of engineering where each component plays a vital role. The engine needs to reach a specific speed before fuel is introduced as a fine mist. This ensures proper combustion and prevents dangerous fuel pooling. The spark must ignite that mist at just the right moment. The engine control unit, ECU, manages this with incredible accuracy. This startup sequence is the result of decades of engineering and hard lessons. Each iteration has improved safety and efficiency. The real challenge is coaxing the engine from a dead stop to a self-sustaining hurricane of power. It's a transformation from inert metal to a roaring force of nature. Once running, the engine powers itself, but getting there requires careful nurturing. It's a delicate balance of fuel, air, and ignition. This is the critical test of the engine's health, where design, theory, and maintenance meet. It's a testament to human ingenuity and collaboration. The startup is what makes crossing oceans in hours possible. It's the foundation of modern air travel. It's a process that never fails to inspire awe. The sheer power and complexity are truly remarkable. To start understanding a jet engine, you need to know its main players, the core components that make it all possible. We're going to take a tour of these essential parts, exploring their individual roles and how they work together in perfect harmony. Up front is the compressor, the first critical stage in this intricate process. A series of powerful, rapidly spinning blades that squeeze the incoming air, forcing it into a smaller and smaller space. This compression dramatically increases the air's pressure and temperature, preparing it for the next stage. This compressed air then feeds into the combustion chamber, often referred to as the furnace, the heart of the engine. Inside, it mixes with a fine, precisely controlled spray of jet fuel, atomized for efficient burning. Special igniters, similar to spark plugs, create a continuous intense spark, instantly lighting the fuel-air mix into a controlled inferno, a continuous and powerful burn. The resulting hot, high-energy gas, now expanded by the combustion, rushes with tremendous force into the turbine section. The turbine, another set of precisely engineered spinning blades, extracts a significant portion of the energy from the rapidly expanding gas, using it to spin the compressor located up front. This ingenious design creates a self-sustaining loop, the key to the jet engine's operation. The turbine spins the compressor feeds air into the combustion chamber, and the continuous combustion keeps the cycle burning. Finally, the remaining hot gas exits through the exhaust nozzle, located at the rear of the engine. The nozzle is shaped to accelerate the exiting gas to an even higher velocity as it leaves the engine. Newton's third law kicks in, blasting the high-speed gas out the back with tremendous force. This action pushes the engine, and consequently the entire plane, forward with equal and opposite force. That's thrust, the force that propels the aircraft through the sky. Each and every part must work in perfect sequence, with precise timing and coordination, for the engine to successfully start and continue running smoothly. The true beauty of a jet engine lies in this elegant, self-sustaining, and continuous cycle of energy conversion. It's a true marvel of engineering, efficiently turning readily available fuel and air into an incredible amount of raw power. Miss even a single step, or if a component malfunctions and the entire process grinds to a halt. But get it right, and you have the very heart of modern flight, enabling us to soar through the skies. The engine can't start itself, it needs a push. Enter the air starter, powered by high-pressure air from the APU, spinning the engine's core. The goal? Get the compressor and turbine spinning fast enough to move serious air. At about 20 to 25% of max speed, the FADEC commands fuel and spark. Igniters fire a continuous arc, ready to light the fuel. A fine mist of jet fuel is injected, mixing with compressed air. The igniters spark the mixture. This is light off. A rapid rise in exhaust gas temperature signals ignition. The starter keeps helping until the turbine can spin the compressor on its own. Once self-sustaining, the starter disengages. The engine is alive, idling, and ready for more. At idle, the engine is just ticking over barely enough power to sustain itself. To reach takeoff thrust, the pilot advances the levers, sending a request to the FADEC. The FADEC carefully increases fuel flow, avoiding surges or flameouts. More fuel means a hotter burn, spinning the turbine and compressor faster. This feedback loop builds power rapidly. Airflow ramps up from a breeze to a torrent. The FADEC monitors temperatures and pressures, keeping everything within safe limits. Inside, temperatures soar, only advanced alloys and cooling keep the engine intact. The engine transforms from a gentle hum to a powerhouse, ready for flight. It's a controlled climb from idle to full, raw thrust. In the realm of modern aviation, most jet-powered aircraft rely on turbofans. These engines have become the workhorse of the industry, powering everything from short-haul regional jets to long-range intercontinental airliners. This is in contrast to their older counterparts, turbojets, which while still in use are less common in commercial applications. Turbojets operate on a relatively simple principle. Air is drawn into the engine, compressed, mixed with fuel, and ignited within the core. The resulting hot exhaust gases are then expelled at high velocity, generating thrust. In a turbojet, all of the engine's thrust is derived from this hot exhaust. Turbofans, on the other hand, incorporate a massive front fan as a key component of their design. A significant portion of the air drawn in by this fan bypasses the engine's core, flowing around it instead. This bypass airflow contributes significantly to the engine's overall thrust, while also making them quieter and more fuel-efficient compared to turbojets. The starting process for both engine types shares some fundamental similarities. Both require the core of the engine to be spun up to a certain speed. This is followed by the introduction of fuel into the combustion chamber and the ignition of the fuel-air mixture. However, turbofans present a unique challenge during startup. The starter motor must not only spin the core but also overcome the inertia of the large and heavy front fan. This increased mass requires significantly more power from the starter and a longer period to reach the necessary speed for ignition. To manage this complex startup sequence, turbofans rely on a sophisticated system known as FADEC, or Full Authority Digital Engine Control. The FADEC precisely controls the fuel flow, ignition timing, and other critical parameters, ensuring that the core ignites smoothly while the fan spools up in a coordinated manner. Despite these differences, the underlying principles of jet engine starting remain the same. The process involves reaching a minimum rotational speed, introducing fuel, and providing a spark to ignite the mixture. Throughout the startup, critical parameters are closely monitored to ensure successful ignition and stable operation. The primary distinction lies in the sheer mass that needs to be set in motion. Furthermore, the FADEC constantly monitors a wider range of parameters to maintain optimal performance and prevent potential issues. To illustrate the difference, think of starting a sports car, which is analogous to a turbojet. Now compare that to starting a heavy truck, which is more akin to starting a turbofan engine. Both require an initial push to get going. However, the turbofan, with its massive fan and complex design, is undoubtedly the heavyweight champion in terms of startup demands. Starting a jet engine is high stakes, so safety is paramount. The FADEC, Full Authority Digital Engine Control, is the engine's brain and watchdog. It monitors every parameter, especially exhaust gas temperature, EGT. If EGT rises too fast, the FADEC aborts the start, preventing damage. It also detects hung starts, engine fails to accelerate, and no light off, no ignition, shutting down fuel and spark as needed. These automatic checks prevent catastrophic failures and keep the engine healthy. The FADEC logs every start for maintenance analysis. Pilots monitor key data, but the FADEC reacts faster than any human. This digital oversight makes modern engine startups safe and routine. It's precision and protection, built in. The air starter needs high-pressure air, but where does it come from on the ground? Enter the APU or auxiliary power unit, a small jet engine in the tail. The APU doesn't move the plane. It powers systems and provides bleed air for engine start. Pilots start the APU first using battery power. Once running, it supplies electricity and crucially high-pressure air. This bleed air spins the air starter, which turns the main engine's core. Without the APU, ground carts would be needed for air. The APU makes the aircraft self-sufficient, enabling quick turnarounds. After one engine is running, its bleed air can start the others, sometimes letting the APU shut down. The APU is the unsung hero, making every engine start possible.